Hello my YouTube friends, today we're going to look at resistive circuits. This is after you've covered what a resistor is, or what resistors do, how resistors are affected by heat, but we want to just look at circuits that involve resistors. So in this study, we're going to look at how to solve or combine resistances in series and parallel. And then we're going to look at how to apply voltage division and current division, as well as how to solve the node voltage method and how we solve the mesh current method. But to add on to that, we're going to also look at the Thevenin's and Norton's theorems and circuits, and then we'll also look at source transformation. But I would prefer to start with mesh analysis and then follow up with node voltage method, as you will see later on. Now let's begin looking at resistances in series. So when resistances are connected in series, what you are going to have is that the same current flows through these resistances because they're connected in series. And the way we find the total resistance is basically adding the sum of the resistances that are connected in series, like you can see here. So to come up with a total resistance for resistances that are connected in series, we simply add, for this circuit, resistor 1 added to resistor 2 added to resistor 3. And you also notice that there's a voltage drop across each resistor, and this voltage drop, by convention, where the current enters the resistor, you've got a positive side of the terminal and the negative terminal. So if we apply Kirchhoff's voltage law, which we will look at in detail, which states that the sum of voltage sources, in this case V, must be equal to the sum of the voltage drops, which is V1, V2, and V3. These must be added to get what we are obtaining here as V1 plus V2 plus V3, which gives us a simplified method to identify how we add resistances in series. So we start using KVL, that is Kirchhoff's voltage law, and using that KVL, which states that the sum of voltages, voltage sources must be equal to the sum of voltage drops in the series connected circuit. And when we do that, we find that because each voltage drop, for instance V1 is equal to R1 multiplied by a current, it's the same current, so V2 is going to be R2 multiplied by I, and V3 is going to be R3 multiplied by I. When we add them together, I, or the current, can be factored out, and what we remain with is the three resistances being added, and that gives us the equivalent resistance. It doesn't matter how many resistors you have in the circuit. All you do is simply add. So in this case, for a series circuit, we are saying the total resistance is simply equal to the sum of the resistances I from 1 to n, Ri. So if we have 10 resistances, we simply add them from 1 to 10 and we get the total resistance. Okay, so now when we look at resistances in parallel, we get a different scenario. In this case, we have the resistances connected, resistor 1, resistor 2, and resistor 3 connected in parallel. And what you notice is that the currents in this scenario are not the same. What is the same is the resistances in parallel share the same voltage. This is what the statement that I've put up here. So you have the same voltage being shared by the resistances, but the current splits. So you have the total current coming into the circuit, and then you've got current 1 through resistor 1, current 2 through resistor 2, and current 3 through resistor 3. And for us to find the total resistance in this circuit, then we have to also look at now these currents or guiders. So we are saying the current in each circuit, I1 is equal to V over R1. So V is common. So we've got V here, which is common, over R1, V over R2, V over R3. And in this case, we apply KCL. So we are saying, in here, we are saying the sum of currents entering a node must be equal to the sum of currents leaving that same particular node. Therefore, if we go further to add up this and applying KCL, this is what we are saying. We are saying the sum of currents, or the sum of current sources, should be equal to the sum of currents in the circuit, or the current splits into these currents, and when they are added up, they should give us the total current. By applying Ohm's law, basic Ohm's law, current is equal to voltage over resistance. So we get voltage, which is common, over R1, V over R2, V over R3. And here we can factor out the voltage here, and we find that we sum up the resistances by this equation, that is 1 over R1 plus 1 over R2 plus 1 over R3. Therefore, the equivalent resistance that we get is basically, if I'm to put it in a different way, sorry for that, if I'm to put it in a different way, we are saying 1 over R equivalent, or 1 over R total, it is equal to 1 over R1 plus 1 over R2 plus 1 over R3. R3, this is 2, R2. So if we add on these resistances, then we get the equivalent resistance for a circuit that has parallel connected resistances. Okay, so the steps that we follow to combine these resistances is, first of all, you start by locating a combination of resistances that are in series or parallel, and then you start to add your resistances far away from the source. And then the next procedure is for you to redraw the circuit with the equivalent resistances for the combinations that you found following step 1. And thereafter, you repeat step 1 and 2 until you reduce the circuit to a single source and a single resistor, after which you can solve for the currents, voltages in the final circuit. And then you transfer these results back into the circuit. As you expand it, you can expand the circuit now. You go back step by step backwards, and you can find the other values of the circuit, that is the voltages across resistances and the currents through other resistance. And then you can check and verify your solution or your answers by applying Kirchhoff's current law in particular parts of the circuit. And then you can also apply Kirchhoff's voltage law to verify that all your solutions are correct. That is, by KVL, you find that the sum of the voltage sources in that particular circuit or in that particular loop must be equal to the sum of the voltage drops. For KCL, you pick a particular node and then notice how the currents are entering and leaving that node. And KCL states that the sum of currents entering a particular node must be equal to the sum of currents leaving that same node. So this is how you verify and see that your solutions are correct. Now, if we begin to look at this example where we're combining resistances parallel and series, you notice that resistors R3 and R4, these resistors are connected in series. This is series, okay? So these resistances are series. Therefore, resistances in series, like we mentioned, we add them. So this will be R, we add them directly, which is R3 plus R4 gives us 5 plus 15, which gives us 20. So this is our first equivalent circuit. So Req1 is simply equal to 5 plus 20. Sorry, 5 plus 15. So you've got 5 plus 15, that gives you 20. And now what you have, if you notice here, we've got, let me change the color, we've got two resistances that are now connected in parallel. So resistor 2 and Req1 are connected in parallel, okay? And for parallel circuits, we know that it is 1 over the total resistance should be equal to 1 over 20 plus 1 over 20. In other words, we are saying we have 20 times 20 over 20 plus 20. This gives us 400, and we have division by 40. And when we do that, we simply get our equivalent resistance here to be 10. So we are saying we have 400 divided by 40, and that gives us 10. And this is how we obtain this resistance. So we combine now these two, R2 and Req1, to obtain Req2. And then you notice that the remainder of the circuit, you've got R1 and R2 connected in series. So you simply add 10 plus 10 to give you 20. That is how you obtain the final circuit, or the equivalent resistance of a circuit. And if we were to now say, can we now find the total current given a voltage across these two terminals, we're able to determine that. So we've used a combination of both series and parallel terminologies or methods to find the total resistance in this circuit. Now, let's look further on another example. In this example, we've got a source which is provided as 90 volts, and then we've got a resistor that is resistor 1, 10 ohms, resistor 2, 30, and 60 ohms. We are saying let's find the total resistance in the circuit, and then we can determine the total current that flows through the circuit, and then we use that instruction or the rule of going backwards to be able to determine the variables across these resistances, variables such as the voltage across each resistor, the current across the current through each resistor. In this case, these two resistances are in parallel, and for parallel resistances, we simply multiply 30 by 60 divide by 30 plus 60, which gives us 90 as the denominator. When we divide into the numerator, we obtain 20. So our equivalent resistance, Req1, is simply 30 times 60 divided by 30 plus 60. When we do that, we obtain our solution to be 20 ohms. So this gives us 20 ohms. That 20 ohms is what we have and what you can see here as Req1. And then what remains now, you've got resistances that are in series, which is simply 10 plus 20 to give you 30 as the total resistance in the circuit. And after we find the total resistance in the circuit, now we can say we have a voltage source here which is 90 volts, and definitely there's going to be a current that will flow through this circuit in that direction from the positive terminal. So if we say that is the current I, then it flows through this circuit or total resistance. And then we can use Ohm's law to find the value of that current, which is the voltage source provided divided by the total resistance, which simply gives us 3 amps flowing in the circuit. And this is what we are able to do when we go here. So we are saying now the total current flowing in the circuit is equal to voltage source divided by the total resistance in the circuit to be able to get 3 amps. And from there we can go back to finding the voltage across resistor 1. We know by Ohm's law that the voltage across resistor 1, or Req1, which we mentioned, if we go back, Req1 is this solution, this resistance, which is 20. So if we find the voltage across this, then we found the voltage across both of these resistances. If you remember, we mentioned to say the voltage across resistances in parallel is the same. So once we find the voltage across this 20 ohm resistor, then we found the voltage across the 30 ohm and the 60 ohm resistor. And this is what we are doing here. And the voltage across the 20 ohm resistor Req1 is, by Ohm's law, V is equal to IR. Therefore the current multiplied by the resistance gives us 60 volts. And we can conclude to say then the voltage across the voltage across the 30 ohm resistor as well as the 60 ohm resistor is the same, which gives us 60 volts because they are in parallel. And then we could use that also to go and find now the current that passes through resistor 2 and the current that passes through resistor 3. So we find that the current that passes through resistor 1, we could also use the voltage divider rule here, but because we haven't covered that, so we'll simply say the current that passes through resistor 2 by Ohm's law is voltage across that resistor divided by the resistance. And we've got 60 volts over 30 giving us 2 amps. On the other side, we have the voltage 60 over the resistance, which is 60, giving us 1 amp. And this we can verify by Kirchhoff's current law, KCL. So we know that the sum of currents entering that node, if I show you, if we go back and we look at this node here. So we are saying, let's pick this node. We know that there's a current entering this node, which is 3 amps. Okay? And then that current splits into 2 currents. You've got a current there, if we say that is IA, and we've got a current there, IB. So when these 2 currents split, and as we have solved, we are finding that the current that is flowing through this resistor is 2 amps, and the current that is flowing through this resistor is 1 amp, which verifies KCL, because we are saying the sum of currents entering the node, which is 3 amps, must be equal to the sum of currents leaving that same node. So in this case, we've got 2 amps plus 1 amp, which gives us 3 equal to 3, verifying Kirchhoff's current law. Okay, now let's go further and look at what we have obtained. So we are saying we verify, and then we can find now the voltages across resistor 1, by basic Ohm's law to be 10 by 3 to give us 30 volts. Okay, so here's another example. Few questions that we have. We've got question combining resistances, that is A, B, and C. Let's look at them shortly, and let's solve and see what we are able to obtain.